So this is the start of chapter 6, which talks about random variables, and in this section in particular, we're going to talk about discrete random variables. So what exactly is a random variable anyway? The first blank here, we can say a random variable takes numerical values that describe the outcomes of some chance process. And I've got a couple really easy examples of that in a moment for what a random variable is. The next blank here says the probability distribution of a random variable gives its possible values and their probabilities. So a random variable in general, let's talk about some examples. So if we flip a coin, right, a random variable that we might be interested in is the number of tails in a certain number of flips. So record the number of tails, that could be a random variable. Another scenario, if we start rolling a die and we record the number of sixes that occur. So that's some random chance process, and we're recording a certain event, the number of sixes that happen. That's a random variable. So a random variable, again, it just takes numerical values. It's a way that we record things that describe the outcomes of some chance process. So there's a couple easy examples. So now let's talk about what is a probability distribution. So for a probability distribution, we can say it describes the possible outcomes. So all the possible outcomes we might see, and how likely each one is. So a probability distribution, it just describes the possible outcomes of an event and how likely they are. So it assigns a probability to each outcome. Okay, so there's two types of random variables we're going to focus on. In these notes, we're going to talk about a discrete random variable. In italics here, it says there are two main types of random variables. Discrete's the first one. The other one's continuous. We'll get to that one later. If we can find a way to list all possible outcomes for a random variable and assign probabilities to each one of those outcomes, we have a discrete random variable. So discrete random variables are things that we can describe and we can list out all of their possible outcomes, and we can give a probability to each one of those outcomes. So we can summarize those two characteristics. For something that's discrete, in this case, we know the exact values for the outcomes, and they're easily countable. So for a discrete random variable, you can think of the outcomes as being fixed. So it's like a fixed set of values, and the things are countable, or you can think about them as like being natural numbers, or in some cases, whole numbers, so without fractions or without decimals. So one example of this, an easy example, the number of children in a family. That's a discrete random variable, right? You can have 0, 1, 2, 3, 4, 5, and so on. Another example, the attendance at a movie. So that's countable, whole numbers, there's no fractions or decimals, we're just counting the number of people that attend a movie. So that would be a discrete random variable. And then one more example, how about the number of defective light bulbs in a box? Stats class always seems to use quality control examples, so this might be quality control at a light bulb factory. The number of defective light bulbs in a box. Again, it's countable. Those are whole numbers, so this would be a discrete random variable. So example 1 has to do with how many languages some high schoolers have the ability to speak. It says, imagine selecting a U.S. high school student at random. Define the random variable x equal to the number of languages spoken by the randomly selected student. The table below gives the probability distribution of x based on a sample of students from the U.S. Census at School database. So here's how we read this. Kids that spoke one language, kids that were randomly selected that spoke 2 languages, and some kids spoke up to 5 languages. And then the probability associated with selecting each one. So the chances you select a kid that spoke 3 languages, only about 6.5%. So part A, when you see a question that says, show that the probability distribution for x is legitimate, show that this thing is a legit probability distribution. There's only two characteristics that you have to point out. So only two things we need to mention here. The first one is that each individual probability is valid, meaning that every probability that they list is a number between 0 and 1, which we should be clear in this case. Right, those are all good. The other characteristic that we have to point out is for this thing to be a valid probability distribution, if we add up all the probabilities, they better sum to 1. So if we add up every single scenario, we should get 1 as our answer. So this one's pretty easy. We can just say, hey, look, all the probabilities are numbers between 0 and 1. They're all valid. But we need to actually show the work for this guy. So we can easily just take each one of these probabilities, add them up, and say this equals 1, so we're all good. So there's two characteristics when you're going to show that something is a valid probability distribution. So part B asks us to make a histogram of this distribution and describe what you see. So on the y-axis, we'll use probability, and on the x-axis, we'll mark off the languages. All right, so let's go ahead and start with our axes. Again, we said probability would be on our y-axis. And I think we can go up to 0.7 here and be safe. And then on the x-axis, we have the number of languages spoken. Okay, and if you remember, a histogram is just like a bar graph that's squeezed together. It's for quantitative data. So the first bar, for one language spoken, we'd say it was 0.63. And then the next bar, for two languages spoken, that was 0.295, so just a hair under 0.3 for the probability. And then three languages spoken was really rare, it was 0.065. Four languages spoken was 0.008. And then five languages spoken was only 0.002. All right, so there's our histogram. That's a really nice way to visually display the data from above. We still have to describe what we see. And the best way to do that is to follow that acronym, SOCS, shape, outliers, center, and spread. So let's start with the shape. This thing is definitely not even close to normal, right? It's got a lot of skew in the right direction. So we can say that this distribution is definitely right skewed. So that takes care of the shape. And as far as outliers are concerned, I mean, all these bars are touching. It's not like I have one way out here. So there's no outliers to note at this point either. And then in terms of the center, we could either mention the median or we could mention the mean. So let's start with talking about where the median would be. I want to remind you the median is like the equal areas point. So if we painted this graph, the median would be where we cut the paint in half. Or another way to think about that would be, where's the 50th percentile? Well, in fact, we have 63% taken up in the first category. So the median, if we mark off 50%, we could even shade this, right? That's half the paint right there. The median would be at one language. And then as far as the mean is concerned, we would just have to estimate at this point, just by looking at the graph. Remember, the mean is like our balance point. If we were to balance this on our finger, it was made out of a solid material. And it looks like, if I have to balance out the tail here, the mean's probably at about 1.5 languages. Okay, so either one of these would work well here. Or you could try to mention both like we just did. Either way, we've taken care of the center. Last but not least, the spread. And the spread's actually, we can just note the range here. So the number of languages spoken actually ranges from 1 to 5. The table didn't report anybody that had spoken 6 languages, so the range would be from 1 to 5. Part C says, what's the probability that a randomly selected student speaks at least 3 languages? Or how about more than 3? So let's just start with at least 3. So that means 3, 4, or 5. So the probability of at least 3 languages, we can take care of that one, plus that one, plus that one. So the probability of a 3, plus the probability of a 4, plus the probability of a 5. So that's 0.065 for the 3, 0.008 for the 4, and 0.002 for the 5. So we're adding up each one of those individual probabilities. And those come straight from the table too, right? For a grand total of 0.075. So there's about a 7.5% chance that you randomly pick a kid who speaks 3 or more languages. Okay, how about more than 3 languages? So the way that's worded, more than 3 means you're really only concerned with the kids who may speak 4 or even 5 languages. But more than 3 does not include 3. So how about just the probability of someone speaking 4 or 5? Well, we would just want probability of 4, which is 0.008, plus the probability of 5, which is 0.002, for a grand total of 0.01, about a 1% chance in this case, of randomly selecting a kid that speaks more than 3 languages. So the reason that example is included is because there's an important distinction there. Speaks at least 3, so that's including 3 and 4 and 5, versus more than 3 is excluding 3. It just wants 4 and 5. Okay, example 2 has to do with roulette. It says one wager players can make in roulette is called a corner bet. To make this bet, a player places his chips on the intersection of 4 numbered squares on the roulette table. If one of these numbers comes up on the wheel and the player bet $1, the player gets $1 back plus $8 more. Otherwise, the casino keeps the original $1 bet. Of course, that means the player lost. If X equals the net gain from a single $1 corner bet, the possible outcomes are X equals -$1 or X equals 8. Here is the probability distribution of X. And something that's important to point out here as far as notation is concerned. Notice when we speak about the whole distribution, that's a capital X, right? X is equal to the net gain. That's the overall picture. And then each individual outcome gets a lowercase x. So just a little stats notation there for you. It's like all the little x's make up the whole probability distribution, the big X. So if a player were to make this $1 bet over and over, what would be the player's average gain? Okay, the nice thing is you don't have to have any idea of how roulette works. And for the most part, I hope you don't. What you do need to know is when you play this game, there's a 34 out of 38 chance you're going to lose. In other words, you're going to lose your dollar. Or there's a 4 out of 38 chance you're going to win $8. So that's where the net gain comes from. If you put $1 down and they take it, that's minus $1. If you put $1 down and they give you that dollar back plus 8 more, then your net gain would be $8. So let's talk about making this $1 bet. Let's assume there's 38 bets. Right? Let's assume a player plays this game 38 times for the sake of, that's the denominator here in our probability, right? We want to know what's the average gain. So average means mean, right? So we'll say mu for the mean with a little subscript of x on it. So what's the average of this game? Or the average gain, if you will. And by the way, don't be surprised if this ends up being a negative number. And let's go ahead and say what x is in this case, right? We need to define our variable here. X is equal to the net gain per bet. So on average, what do you expect it to make per bet? So then the mean, and remember we're going to play 38 times, we're expected to lose 34 times. So we lose that dollar 34 times. I don't want to write out all 34 times, so I'm just going to put ... And just so you know, we have 34 losses here that we're expected to make. And then we're expected to win $8 for those opportunities. So there's 34 and there's 4, so there's a 38 outcomes out of a total of 38. Okay, so let's simplify this a little bit. that negative 1 happens 34 times. So negative 1 times 34 plus the $8 win happens 4 times. Now this is easy enough to calculate, but I want to demonstrate a point here. If I can just split this fraction, meaning put this front part over 38 and then the back part over 38, if I could just split this for a moment, that'd be negative 1 times 34 over 38 plus 8 times 4 over 38. Hopefully you believe that. That's definitely true as far as the math is concerned. And then one more simplification I want to make. This is the same as negative 1 times 34 over 38. And this is the same as 8 times 4 over 38. So the reason I wanted to demonstrate that for you is to show you the rule. If you want to know what the mean is, all you have to do is take the outcome for negative 1 when you lose $1 and multiply it by its probability, plus take the outcome for $8 and multiply it by its probability. And our average net gain per bet, we're actually expected to lose 5 cents per bet. And just as a reminder, that's in the long run. If we play this game over and over and over and over again, on average, after all those bets, it will look like we've lost 5 cents every time we played it. Okay, so to summarize, how do you calculate the mean, or the expected value as it's called, of a discrete random variable, and is the formula on the formula sheet? So mu sub x, right? X is our discrete random variable. Mu is the mean. So the mean of x, and what I tried to demonstrate in the last example was you just multiply each outcome, whether it was win or lose, by its probability, and then you add up all those products. Is that formula on the formula sheet? Sadly, it's not, right? And it's really not necessarily a formula, right? I just told you how to come about calculating it, and we demonstrated it with an example. So example 3 says calculate and interpret the mean of the random variable x in the languages example on the previous page. So if we go back to our languages here, if this is our x distribution, right, then the mean of x, the mean number of languages spoken, we would take 1 and multiply it by its probability, plus we would take 2 and multiply it by its probability, and so on and so forth. So let's go ahead and do that. And instead of just using x's or letters in general, we can just say the mean number of languages. So we've got the mean for the languages equals 1, right? There are 63% of kids, plus 2 languages times 0.295, plus 3 languages times its probability, plus 4 languages times its probability, and then 5 languages, which should give us a total, after we add these up, of 1.457 languages spoken. Okay, and then the last little bit for these notes here. Does the expected value, or the mean, of a random variable have to equal one of the possible values of the random variable? Should expected values be rounded? Well, if you look at 1.457 languages, that was definitely not on our chart, and you shouldn't expect it to be. So the last note I have for you, when you're doing the mean or the expected value for these random variables, they can definitely be decimals, right? They don't have to be one of the values on the table. And as far as rounding, just try to be as exact as you can. So maybe 3 or 4 decimal places, and you'll be good. All right, so we talked about what a random variable was, in particular, what a discrete random variable was, and how to get the mean for a discrete random variable. So that is all for these notes. I'll see you in class.